Then let's go beyond this a little bit. So we have A atom move into a vacancy, A atom move into a vacancy, A atom move into vacancy. We can treat it as if that vacancy move back, right? A moves to vacancy. We can treat it as if the effect is V moves back to A. Okay. So now let's consider we have this material. They have both A atom and B atom, and we said okay, they are different. They are so-called intrinsic diffusion coefficient. dA is greater than dB. Copper is different from zinc. Zinc may have higher diffusion coefficient than copper, and JA prime would be larger than JB prime. I put absolute value because JA and D are related by the concentration gradient, but that concentration gradient is the same value for A and B. For absolute value is the same. So then we would think, okay, for A atom to move from 1 to 2, it would create a effective vacancy flux. A atom moves, that will create a effective vacancy flux, JA prime, but minus. JA prime means what? JA means flux of A atom. Prime means it's with respect to my so-called chosen lattice plane. Okay. A atom moving towards right. At the same time, I would have an equal value but opposite direction of a vacancy going backward for A atom motion. Similarly, B atom moving backward, and I would have a negative value equal amount of vacancy due to B atom motion. Okay, so the so-called net flux, not of atom, net flux of, read to yourself, vacancy. A moves, that's effective, some vacancy moves backward. B also moves, there will be some effective vacancy move due to B element. The net flux of vacancy with respect to my chosen marker or chosen moving interface would be minus JA prime plus minus JB prime. Again, JA prime is for what? Flux of A atom with respect to the moving interface. JB prime is the flux of B atom with respect to the moving interface. But I negative, these two are for the opposite vacancy motion. And since both are for vacancy motion, I can add them up together. The total net vacancy would be this. Okay? So if we know JA prime, previously from fixed first law is dA partial differential of concentration with respect to the moving coordinate location. Similarly, JB prime. What is JB prime? dB times concentration gradient, of course, with B. And from previously, remember, partial differential of CA with respect to X and partial differential of CB with respect to X, they are opposite sign. So that's why I now have a positive sign here. I go from B to A, but I remove the negative sign. You see it? So if we are going to write it together, the net flux of what? Vacancy. Because A is going one way, B is going the other way. A moves, cause some vacancy to move. B moves, also cause some vacancy to move. But net flux of vacancy due to this is given here. Okay? And then JA prime minus JB prime. I put it in, negative sign cancel. right? CA prime, CA prime, C X prime towards the end, minus dB, minus dB here. See it? Minus dB, minus dB. Minus minus dA become positive dA. And the differential term here and here are exactly the same. Okay, so this is the net flux. What does this tell you? If dA and dB are the same, what would happen? If dA and dB are the same, what would happen? The net flux of vacancy is 0. Makes sense, right? If this guy and that guy is exactly the same, then the net flux of vacancy is also 0. Makes sense, right? Okay. Now, the vacancy net flux to that vacancy plane, that's what we said. The JV prime with respect to that moving interface is dA minus dB times partial differential concentration gradient with respect to X prime. Remember, X prime is the location within that moving bus, moving coordinate system. Okay, so that's what we said. And then now define how fast your bus, your moving interface move. We define it as U. The velocity of what? Of that moving interface. Because we remember we said in Kirkendall did the experiment, the Molly wire would move. That indicates that interface actually moves. That chosen lattice plane is actually moving. How fast does it move? Let's define it as U. Velocity. Okay. And then we are going to have this relationship. U, how fast does it move? It's related to JV prime and C0. What is C0? The total number density. Number density. How many total atoms per unit volume? And the JV prime is the net flux of V for vacancy with respect to that moving interface, and velocity are related together by this relationship. Let's just check the unit. What's the unit of velocity? Meter per second. What's the unit of JV? Number per unit area, meter square per second. And what's the unit of C? It's number per meter to the power of 3. So because meter to the power of 3 we flip up, right? Let's see the meter power of 3 flip up, and this J is per area. I would have a net meter on the denominator, and I should still have a second in the denominator. So that at least from dimension point of view, it makes sense. It's JV flux divided by concentration. That's how fast that lattice moves. That lattice plane moves. If dA equals dB, what would happen to JV prime? Based on this equation, if dA equals dB, what would happen to the JV prime? 0. And if JV prime is 0, the lattice plane motion is 0. Make sense? If there's equal amount of diffusion, my lattice plane, there's no net flow of vacancy, and my lattice plane doesn't move. Makes sense, right? Now it makes sense. Okay, and what is JV? JV from here is dA minus dB, partial differential of concentration with respect to the moving coordinate location at C0. Make sense? So now we did some manipulation. What did we do? We put dA minus dB in the front, and then we put a C0 beneath what? We put C0 is a constant, right? We can put C0 below, beneath what? CA, right? From here to here, I put C0 beneath CA, and I put partial differential of X prime still down here. Make sense? And then Ca divided by C0, do you see that is just your so-called molar fraction? Ca, the number of atoms per unit volume of A divided by C0, the total number of atoms per unit volume. That would give you so-called molar fraction of A with respect to location, but it's, remember, it's on your moving coordinate, on your bus. Make sense? That's our mathematical manipulation. And then at time t for velocity u, your bus is moving, remember? Your moving lattice may be moving. The relationship between the two coordinate systems, one is your fixed, external fixed coordinate system, which we call x. The other one is within your bus. Do you see the coordinate system x would equals to x prime plus ut? When u is 0, which means what? U is 0 means velocity is 0, x would just equals to x prime. Make sense? And then when t, for fixed velocity, when t goes longer, the displacement is larger. That's just a linear transformation. Make sense? So then as a result, do you see that this velocity would be just dA minus dB xa small x prime when we are doing this what? Manipulation. X prime is still here, but partial x denominator, partial x in the nominator, right? I just put it here. And what is the partial x with partial x prime from here? It's 1, right? The partial differential of x with respect to x prime, take this versus that, it's just 1. As a result, that's our velocity, moving velocity. We would have u for velocity of my chosen lattice plane, or my reference point. It's moving at this speed. Okay? This is our so-called Darken's equation, the first Darken's equation. The first Darken's equation. Again, when dA equals dB means what? Based on this equation. 0. That moving lattice doesn't really move, has 0 velocity if they are diffusing in an equal fashion. Make sense? Okay. And what this means is this velocity is the collective flux of atom due to this lattice plane movement. Remember that lattice plane is moving at this velocity. The collective flux atom A due to the lattice plane moment would be concentration or number density of A atoms times its velocity. JA for what? Flux of A, but I put double prime. Double prime means it's a flux of atom, but due to this lattice plane motion, for what atom? For A atom, it's just the concentration, the number density of A atoms times this how fast this lattice plane moves. If the lattice plane velocity is 0, this term goes to, if U goes to 0, this term goes to 0. But if the faster this lattice plane moves, it means collectively all the atoms would move also at this velocity. Okay? And then if dA is greater than dB, dA is greater than dB, and x is partial differential concentration is smaller than 0, the velocity is actually negative. Which means, okay, A side, this gradient is negative, which means the left side may be higher in A, the right side is higher in B. Higher in A goes towards B, and if dA greater than dB, the velocity, actually everything moves backward, negative. Okay? So then let's consider the total flux. Maybe you got confused. The total flux, the atoms is moving. Atoms are moving. The total flux of 8 atoms will be 2 parts. The first part would be the diffusive part, the random motion of 8 atoms. With respect to what? Relative to your chosen lattice plane, your reference, moving reference point. The total flux is whatever I'm referring to with respect to my chosen plane, which is given by the fixed first law, dA, intrinsic diffusion coefficient, and concentration gradient with respect to the local moving coordinate, which is the same as the stagnant coordinate, plus another term. The other term is, okay, the vacancy is moving. And as a result, my lattice plane is moving. And as a result, all the 8 atoms together is moving. Because my lattice plane is moving. You think your bus is moving. All the kids inside is also moving together with the bus. At the same time, the kids inside are mingling. So the total, if I'm tracking the boy movement would be how fast the boy moving together with the bus plus how fast the boy move within the bus. Make sense? That's just the 2 part. So this is the second part. The flux of A atoms due to the moving interface is Ca times U. The total flux is 2 part. Randomly diffusion, which is how, if I'm going to put an analogy, how much the boy within the bus moves. And what is this term? This is how fast, it's not a perfect example, but it's kind of like how fast the boy together moves with the bus. Okay? So the total flux is these two combined. The J prime plus J double prime. J double prime is Ca times velocity. Okay? And then record what is our velocity. We said velocity from Darken's first equation is just the difference between the diffusion coefficient times the concentration, the molar fraction gradient. Okay? And then, mathematically, now that's just pure mathematics. What is our JA prime? JA prime. JA prime is just this term, right? It's minus dA. JA prime is minus dA times what? Partial differential of Ca with respect to x plus the Ca times U. Ca here. Within the square bracket is U, or the velocity of that moving interface. Okay? And then let's expand it out. The first term we keep. dA minus dB we keep. Ca, that's what we keep. Okay? Now let's do the mathematical manipulation. The first term, dA, we put a minus sign. That's the first term. And then the second term, dA times what? Xa, right? dA times Xa, what sign? dA times Xa, positive sign. But if I'm going to put a negative sign in the front, I have to put a negative sign here. The third term, dB times Xa, dB times Xa, what sign? Negative sign. If I'm putting a negative sign here, that means it has to have a positive sign. And what about this differential term here? Cax, Cax, it's the same, right? So that's this final differential term. And then let's combine this guy and this guy. dA, we put it in the front. 1 minus Xa, that gives us what? Xb. And the second term dBxa we keep. So that's what we are going to have. The net flux of A is minus dAxB plus dBxa times this so-called concentration gradient. So this is what we have. Sorry. The flux is this kind of an interesting crossing term. dAxB plus dBxa times concentration gradient. And if we define so-called inter, because we are dealing with A and B, we are dealing with alloy, interdiffusion coefficient, d delta is dAxB plus dBxa, then the net thing, this whole thing we call it Darken's equation, d delta, and the generally dA delta is not the same as dA, not the same as dB. Okay, which are so-called intrinsic diffusion coefficient. And then the total flux of A with respect to the specimen external coordinate or end surface, looking outside, not in the bus, looking outside, stand on the ground. The total flux of voids or the A would be JA is d delta times concentration gradient. And this equation we also call Darken's equation. And similarly, we can get the same derivation for JB. The total flux of B would be minus d delta partial differential of CBOX. Remember, what's the relationship between CA and CB? CA at CB equals a fixed value, which means when we do concentration gradient, it's just opposite. What does that mean? JB, the net flux with respect to external coordinate would be the same as minus JA. No large change in location, which means when Darken did the experiment, that whole block, brass plus copper, doesn't move. When you look outside, nothing really moves. But when you look at that interface moves, and across that interface, it's moving in asymmetric fashion. Okay? And then we would have fixed second law rewrite if we're going to use the diffusion coefficient, that's so-called interdiffusion coefficient. Okay? Let's stop here.